So hopefully without too much further ado, we'll be hearing from Aaron Goldberg, U of T alum now at NRC, about something that I saw a second ago and already forgot, although it's making impossible measurements with indefinite causal order.
Thank you very much. Thank you for the introduction, and we will get started in a minute. But by way of introduction, my name is Aaron Goldberg. I am from the National Research Council, which is on the traditional unceded territory of the Algonquin, Anishinaabe, and Mohawk peoples. And this is work done at NRC and also while I was at University of Ottawa for a postdoc fellowship. So we are good to go. Excellent. Thank you all. So the forward moving button. I'd like to start with acknowledgement. I'll be telling you about some things that I think should be impossible to measure. It turns out they're not impossible to measure. And with the help of certain great people, we are doing that. So we've got theory collaborators, Chabat and Luis, who are what's a bit hard to see. You've got NRC, U Ottawa, Madrid, Erlangen, experiments. We have Griffiths and Queensland, mostly started by Andrew Wright and Sergei Slusharenko. And together, I'll be giving you this hopefully full picture of some things that you think shouldn't be possible to measure and how we can make them possible to measure. So the idea is, why do we care about measurement at a quantum information conference? It's because quantum theory promises that you can measure some things better if you use quantum systems than you could do if you didn't use quantum systems. And the way that this sort of works is that as a theorist, I describe things that you want to measure as parameters. So we have this data up here. It could be a magnetic field, it could be an electric field, it could be a speed, it could be a position, it could be a distance. And you want to measure these things well, which means you want to have the uncertainty, the uncertainty in whatever parameter it is go down. And it turns out that for some type of resource, let's say it's the number of times you repeat the measurement, classically, you can get the uncertainty to go down when you increase that resource with n. And it turns out that there are certain quantum mechanical resources that let you do experiments, that let you get information more efficiently with that resource, which is useful if either the system you're trying to probe is very fragile, it's very expensive, you can't interact with it for very long, you're limited in how many times you can look at it. If you can get enhanced precision, you will be very happy. So my example up here, which is hard to see with the color scheme, and I apologize for that, is let's say you want to measure the temperature of a star. You start out with your thermometer in some initial state, you put your thermometer in the star, you hope it works. The thermometer changes, this column of mercury goes up, and then you measure how many centimeters tall the column of mercury is, and you feed that into a theory to deduce what the temperature of the star was. And it turns out with quantum probe states and quantum measurement, you can be more precise in these things. The problem is that with everything we know, noise ruins quantum advantages. So here I had this resource and I have this noise scaling, and it looks like they're doing the same thing. But here, this noise scaling with this parameter p you could think about as like the probability that your experiment works, and we'll get into exactly what it is. But this is a number between 0 and 1. So if your experiment is perfect, p for perfect maybe, you would get back the uncertainty you started with. But if p is small, then your uncertainty goes up a ton, your variance goes up, noise ruins your quantum advantages. So what I'll be telling you about is a way to withstand noise, get back quantum advantages for sensing, and use this fancy thing called indefinite causal order that we will get into. This is what I think about when I think about a background in quantum metrology. So you're measuring the temperature of a star. You start out by preparing a probe state. And that probe could be anything. It could be a receiver that's ready to receive some signal from outer space, or it could be you were shining light on something, then you're going to collect the light that's reflected back. And through some interaction, that interaction imparts on your probe or on your receiver some parameter, set of parameters, and those are the things you're trying to measure. Like it changes how tall your column of mercury is, and that's the thing that you'll then use to infer the temperature. So you have a final state that depends on the parameter. On the final state, you do some measurement that gives you classical data, and from those classical data, you then try and infer what the actual value of the parameters were through something like classical estimation theory. You have maybe calibration data that say, for this length of mercury, we associate it with that temperature. And you could have theory, you could have calibration, and each of these steps has been optimized. If you want to know what the best initial state is, you use something called quantum Fisher information. And the theory of quantum Fisher information tells you how to look at a state and evaluate how good that will be in trying to estimate any set of parameters. So that's been optimized. You can use it on classical states, quantum states, it all works. The measurement that you do, there are lots more measurements you can do in quantum theory than classical theory, but the former encompass the latter. And if you want to find the best possible measurements you can do on a state that's evolved to glean that information that the state has been imprinted on the state, quantum estimation theory started by Halevo and Hellstrom really tells you what the optimal measurement is to do. So that's all been done. And then once you have data, this is all classical estimation theory, and how to optimize going from data to a guess of a parameter has been optimized. And it looks like everything's been optimized except for this step of actually changing the dynamical process. That's normally taken to be fixed, where there's an interaction and that interaction is given, and you want to then use the best thing of figuring out what can happen, how that can change the temperature of your thermometer, how the star will impart some information. The dynamical process seems to be fixed, but we want to change that dynamical process in such a way that we can do better without actually having to control the physical state of the system whose temperature we're trying to measure. So the way we do that is using something known as indefinite causal order. Indefinite causal order is best understood through this quantum switch model, where you have a quantum state that dictates the path or the order in which two operations happen on some other quantum state. So in this image, what we have is there's a control system and a probe system, and they can both be quantum or they can be classical. They can do whatever they want. If the control is in a particular state, then the probe traverses these arrows and goes through A, and then B, and then out. And throughout all this process, the control just sails along on the edge on the top here and doesn't experience operations A and B. And that's fine. And you can have a different state for the control, where now if the control is in some state 1, then the order in which the operations happen on the probe is first going through B, and then A, and then out. This can be done classically, it can be done quantum mechanically. You can have a coin and you flip a coin to decide what is the order in which two operations happen. In our first presentation of the day, we got into how you can use a quantum system to dictate whether photons get shuttled through the lattice site or not. And the control can be in a superposition state as well. And so not only do you have I do this or I do that, or a probabilistic mixture of the two like a classical coin flip, you can also have your control state that's dictating the order in which your probe goes through operations A and B. You can have that control state be in a superposition, and then you can get interference terms between these two evolutions that give rise to novel physical properties that you can use to advantage. So here what we do is we never actually change how interaction A itself works or how interaction B itself works. But if you control the order in which your probe state sees those two operations, you get a new set of interference terms. And as you'll see, these interference products can give you extra quantum advantages, even if you had already started with the best possible quantum probe state for doing some operation. You can do better if you add in this extra type of dynamics. So in math, because I showed it to you in pictures and I said it in words, in math, the way you would describe this is that the overall operations on your system are coherent. There's still a unitary operation acting, and it operates on two different physical systems. You've got the control system and you have the probe system. And just saying in math the same thing that I've said in words and in pictures, you say if the control is in state 0, then operation A happens before operation B. If the control is in state 1, then operation B happens before operation A. And if you have some sort of superposition as your control state, you will get interference terms between these two. So if you have something like a plus state, an equal superposition of 0 and 1 for the control, people refer to this as indefinite causal order, where the actual order that the system experiences operations A and B is indefinite. It can't be ascribed one causal order or another. But overall, everything's coherent. We first got interested in these things, and because other people got interested in them, that's how these things work. We didn't invent it, but I want to say, it says 2012 is the first thing here, but say late 2000s, the first people started thinking about quantum computation, where the structure and the physical connectivity between the gates and the wiring could be put into superpositions, or have a different quantum system control the order in which operations happen. And through exploring that, people have come out with quantum advantages beyond quantum advantages in the big three: computation, communication, metrology. And these are very exciting. So I give pairs of theory and experiment for these examples because they've all been done. People have these exciting ideas and then show that they're useful. So at a CQuick conference, I might as well mention these other possibilities. I come from this metrology background, but just to mention what else exists out there. If you want to send information through a completely depolarizing channel, it should be impossible. There are channels that are so noisy that they wipe out any information you send through them. And it turns out that if you use this indefinite causal order thing to send your state with some quantum information through two different completely noisy channels that will destroy all quantum information, but use a superposition of the causal orders in which you send through these two channels, you can actually retain some information after you send it through. You can do quantum computational things where if you have some oracle that you need to use to do a computation, and you want to say, how many times do I have to query this oracle in order to solve some calculation? It turns out that if you just keep querying the oracle one time after another, it's not the most efficient way possible. And using superpositions of the order in which you do one part of your computation and a query, another part of the computation and a query, you actually can use fewer queries and reduce the computational complexity of doing particular computations. And similarly, for particular measurements, where you had this progression where some resource increased your precision or decreased your variance as this resource increased, classically you had this 1 over n, and quantum mechanically you get this 1 over n squared. For a particular type of resource and a particular type of experiment, it's possible to get even better scaling if you use this indefinite causal order thing, and I'd say this is the most recent one on the list. This is where we started to get excited about indefinite causal order. These are all very specific examples, but that's also true with Shor's algorithm. We have specific examples that get people excited about quantum information theory, and then the goal is to say, how can you generalize these? What else exists out there? What types of quantum advantages are there? And the one we're looking for is using indefinite causal order to find a quantum advantage in noisy metrology, which is this one I said right at the beginning where noise ruins quantum advantages. And we want to say, does this superpositionness in the order in which you go through different noise channels and the thing you're trying to measure, does that give you a quantum advantage? And the reason I'm here is because it does. So this is my setup. Suppose you're trying to measure, this is all physically exactly true, but you can also use the analogy and just call it an analogy. You have some Rubik's Cube, and you're trying to measure which side got rotated. And you want to measure by how much it got rotated. That's very easy to do if you know what state if you know the original orientation of your Rubik's Cube and you know what happens after. It's very easy to distinguish what happened and how it changed. You start out with, say, this very ordered state, you can tell what side was switched. But if somebody comes and mixes up that cube before the rotation happened in the middle, or mixes up the cube after the rotation happened in the middle, it should be pretty much impossible for you to figure out what happened in the middle if you don't know what the mixing was. If somebody just randomizes the cube, either before or after, it should completely ruin everything you can find. What we said is, let's say you do both before and after this mixing happens. That should ruin things a lot. But if you can do the before and after mixing of your Rubik's Cube, and you use a quantum system to control the order, whether you do the mixing of A first, and then the rotation, and then the mixing of B, or the mixing of B, and then the rotation and the mixing of A, and then you go out, it turns out then you can withstand a lot more mixing noise, a lot more uncertainty that you might have thought would go in is something you can still withstand and learn what that rotation was. And to make everything even more in your face, we'll say, let's say we'll actually make you start out with a completely mixed state anyway, whose orientation you didn't know, so that it really should be impossible to measure anything. And at the end of the day, we'll say you don't even look at the cube that comes out. You just do a measurement on this control system that sailed along by and went away. And you only have to do a binary outcome measurement. You just do a single shot. Through all of that, you can still learn things just because of these indefinite causal order strategies. And how much can you learn? And this is the theory result, so I'll put in some math again, but I'll tell you it in words at the same time. The theory result is, if you're trying to measure this thing that I call a rotation, it can be any unitary operation that you want. And to start out, we'll say you're measuring the phase of a unitary. So you have any unitary you want, and it's parameterized by some Hermitian, you've got some Hermitian generator, and then you have a strength. So this could be like a magnetic field strength, it could be an interaction time, it could be a propagation length. You're trying to measure that thing, and it's the phase of the unitary. And there is an optimal quantum probe state to use to do this measurement. But what we do is we subject your probe state to some mixing where you keep your state with probability p, that's the p from before, and you get a completely mixed state with probability 1 minus p, and that completely mixed state is very bad for sensing. If you do this both before and after, then your uncertainty will do badly when p gets smaller because you're just losing information, and it sort of starts to blow up with both the before and after mixing. It doesn't matter which is before or after if it's a definite causal order. With the indefinite causal order, and with our in-your-face state that we said you start out with a maximally mixed probe, we get also a scaling that gets worse with noise, but gets worse at a much better scaling. So instead of the product of PA times PB, we get the sum of PA plus PB, still to the -2 here. So what does that mean? If you look at the ratio of two uncertainties for two different protocols, the ratio tells you how many more times you'd have to do one protocol to get the same precision as doing the other protocol one time through, say, the central limit theorem. And what that means is so we can talk about this mathematically as a quantum Fisher information ratio, but I also treat this as just like the ratio of the number of times you would have to do the definite causal order best possible quantum measurement versus our indefinite causal order measurement with the maximally mixed probe. As this p parameter goes down, the ratio becomes huge. It goes up to infinity technically. And what you find out is that you get an unlimited advantage for using the indefinite scheme once the noise level is very high. So to say that again, in different words, to put it into stark contrast, we have these two different scalings with the loss parameters. And if the two loss parameters are the same, then we do better with indefinite causal order by this factor of p squared. And what that means is if you try and get the same precision, we'd have to repeat the experiment p squared fewer times. And if p is small, that can be a huge advantage. If the two noise levels are different, then it's actually even a bigger advantage for us. Let's say one of the two noisy channels was completely noisy, lost all information possible, so something like PA equals to 0, then without indefinite causal order, with definite causal order, there's no way you could ever learn anything. It's completely depolarizing. There's no way you could ever learn anything. But for us, you add 0 to a non-zero number, and you get a non-zero number, and you can still learn something about the parameter. So in the equal case, I put like a spin 4 particle, because why not? And you're doing some particular thing. But it turns out that the equal mix in this case, which looks the easiest theoretically, is actually the most generous to the definite causal order. We can do indefinitely, we can do as much better as you want with the indefinite causal order. So I put up the slide to say, did we get lucky? The answer is no. This works not just for measuring a particular phase, it works for any unitary. It works not just for this depolarization noise, it works for amplitude damping, it works for dephasing, it works for measuring more than one parameter at a time, it works for measuring noise parameters. So really what I'm here to tell you is that changing the dynamical process actually makes a huge difference and is pretty useful for quantum metrology. If you want to then go and do an experiment on this, which is in the works, what we do is we need a probe state and a control state, and you can use anything you want. So you start with the simplest thing, you make them each qubits, and what you need is a control state that can dictate the order in which your probe traverses a circuit and sees the different operations, which is a little bit hard. And what you want is the control to not be affected by whatever acts on the probe, while the probe can have, say, depolarizing channels and unitaries acting on it, which seems like a steep task, but it turns out people have already done experiments in this realm, and if these experiments exist and they've been done and they've been published, then those ingredients already exist. It can just be applied to our protocol. So what's been done in this paper from, I guess, 6 years ago now in Andrew White's group is they decided to use both the probe and the control to be different degrees of freedom of the same photons. And what they did is they said, if you use the polarization degree of freedom as the control, then you can use that to set up a nested interferometer so that the photons go in different places depending on the state of polarization. Then in those different places, they have the extra degree of freedom is the spatial mode of the photons, and you could subject them to unitary and depolarizing channels, and you can do all the measurements, and it's great. And so for that, I'm going to switch to some slides that Andrew White made for showing exactly how this experiment is proposed to work, parts of how it's already working, and then we'll not get to final results yet, and you'll have to stay tuned for those. So the idea of using polarization as the control is that you set up a polarization interferometer where you start out with light incident on a polarizing beam splitter, and depending on the polarization of the light, it will either be transmitted through the beam splitter or reflected off. And so if you start out with here diagonally polarized light, then the horizontally polarized component goes through and the vertically polarized component goes to the left, top left, and you have operation A in one path, operation B in another path, the unitary in a separate path, and depending on the polarization, these things will go around in different orders. So you start out by tracing out what the horizontally polarized light will do. It goes through operation A, it bounces off some mirrors, it sees another polarizing beam splitter and keeps going through, and then keeps bouncing around, goes through operation B, sees that original polarizing beam splitter again and keeps going through, sees that second polarizing beam splitter again, second is a loaded word, and then goes out. You can trace the same thing for the vertically polarized light, which bounces off all of the polarizing beam splitters. So it does a first bounce, and then it does a second bounce, and it gets back to the first one again and goes through a third bounce and comes out. And if you look at the order overall, each one goes through channel A and unitary and channel B, or the opposite order, always through the same orientation. And the stuff that you have to put in the middle is going to act on the spatial modes that will change the probe system, if you will, and what's interacting with them. So a bit of a simulation, but definitely a quantum mechanical demonstration. This is what's already been done in the lab. So it's the same setup, but without the unitary U. So you have this nested interferometer where the polarization tells you whether you're going through all of the polarizing beam splitters or whether you're reflecting off all of them. And the only addition that we need is to put a U over here, and then exactly the protocol will have been done. The setup here says that there are a bunch of components that have to compensate for stuff. So these half-wave plates and quarter-wave plates have to compensate a little bit because the control degree of freedom is not supposed to be affected by the stuff happening in operation A or operation B, but it gets affected a little bit in a known way, and so that can be compensated for. All of these lenses and rotating prisms are the ones that act on the spatial modes, and they're duplicated on both sides. Then at the very end, if you want to measure the control degree of freedom, you use a wave plate and a polarizing beam splitter to measure in the polarization basis. What's important about this picture, that's not really in the picture, is that the coherence length of the photons going through this are actually long enough that they cover the whole interferometer. So in some sense, you get around some of the small challenges of people saying, well, you're not actually seeing the same unitary, you're not actually seeing the same operation because the photon was too short and they were probing them at different times. But if you can say that the operation, if you can say that the thing that they were probing didn't change enough over time, or you were coherent enough that you saw everything at once, then you can get around some of those contentions. So as a talk telling you a bit more about the experiment, if you're familiar, you probably know how to change polarization of light. You use these familiar optical components of quarter, half, and quarter wave plates. And on a Bloch sphere, what you do, here I guess horizontally polarized light is on the left, that's great. What you do is you move this qubit around somewhere, and depending on the orientations of these wave plates, you change the path that your qubit takes around this Bloch sphere, or in general, you change how the Bloch sphere is rotated. The same exact thing works for spatial modes as well, but if you want it to be a qubit, you need to define a qubit basis. And here, the idea is to use two Laguerre-Gauss modes, where these two Laguerre-Gauss modes carry different amounts of orbital angular momentum. This is a kind of like a spatial version of spin angular momentum, if you like that. And they can be in superposition, and there's an analogous physical transformation using lenses instead of wave plates that do the same thing. And so you get the same full programmability. It's not exactly as clean. You need to worry about beams diverging a little bit more. It's not as clean, but all those operations work. And to say it explicitly, if you want to know how a wave plate works, it's got some birefringence so that different polarization components travel at different speeds, the different propagation length, they pick up a different phase. So similarly, if you want to do some sort of rotation of a Bloch type sphere, but now for the spatial mode, you need a setup where you get a different phase accrued onto different basis states. And that's what a rotation of a qubit is. So that's what these cylindrical lenses do. And the Dove prisms work by inverting the polarization, and so you can rotate the spatial mode. You need to have a relative phase in two separate bases in order to get full rotations around a sphere. And so combining these two components can be done. There are extra technical details that I'm not an expert in, but these extra technical details say that officially you're supposed to be able to control the spatial modes or control the polarization modes without talking to each other, so that they can be independent, say quantum or even classical degrees of freedom. And technically, it's not perfect. And so extra compensation needs to be introduced to fix those things. And that's why there are extra wave plates after what was supposed to be only acting on the spatial modes. And that's okay, because it can all be completely figured out and it'll do everything you want. So to make this a depolarizing channel, what you do is you take these here they're rotating prisms, and you rotate them physically. And if you rotate them fast enough, then, and if it's faster than the time scale in which your detectors can actually measure those photons, then it'll effectively depolarize, not the polarization, but the spatial mode, and you can get complete noisiness added to your system. And then if you want to have the unitary operation, you'll put something like this in the last arm, but you won't rotate them randomly. They'll just remain fixed, and that will be what you want to measure. That's the setup. The last thing to do is to put this really in your face, is trying to start with a maximally mixed state as the probe. And the maximally mixed state as the probe is just for fun, to show that you would think that should be impossible to measure anything with, but we can still measure something. Turns out it's not so easy to make a maximally mixed probe state where the control is still pure, and yet the same photon. And so this is really what the experiment was stuck on, because all the other components already exist in the lab. These experiments have been done. So this is the one, I'd say, interesting insight that you might be interested, where you're trying to make a pure control, a mixed target state in the same photon. And the idea that they had was, let's make the maximally mixed state in the polarization degree of freedom, and then transfer it to the spatial degree of freedom, and then we'll just purify our polarization again, and we'll be done. So the idea is you first start with everything pure because you have a nice laser or you have a nice single photon, and you send your system through a birefringent crystal. And by doing that, the vertical, I'll scan back and forth a few times so you can appreciate the difference. There's a different delay for the different polarization components of your light. And if you start out with a diagonally polarized beam of light, you get both of them together, and you set it up in such a way that the phase delay, the propagation length difference between these two components is longer than the coherence length of your laser. And then you've effectively completely decohered in this polarization basis. And so your pure diagonal state that you started with becomes maximally mixed in this polarization in any basis that you want. That squinting is what you want. And so if you don't do that, people have done this, and this has been done a long time ago. And if you do this a long time ago, the numbers were 99.6% 25 years ago. If you do this, it actually works. The next step would be, once you've done this in your polarization, how can you convert that to your spatial mode? And there, what you do is you use a Q plate, where a Q plate transfers and is like a swap in some sense, depending on the rotation. It transfers spin angular momentum to orbital angular momentum. And this lets you take your maximally mixed state that you made in polarization and give you a maximally mixed state in the transverse spatial mode. I don't believe part of this slide, so it's possible that only one will be mixed and not the other, and there are some ideas about putting a polarizer in after that, but just take my word for it that you can do the transfer of the maximally mixed state from your polarization to your spatial degree of freedom, and then we're going to need a little bit more tuning for what to do with the polarization degree of freedom left for making it pure again. That's as far as the experiment has gone, and that'll give us lots of time to stay on schedule. So, in conclusion, I really want to drive home the point that not just in metrology, but across quantum information, this indefinite causal order stuff gives you new types of advantages that I think are a new way to think about quantum and maybe a new place to look for applications. In metrology, it can help you withstand noise, and noise was normally this bad thing for metrology, so withstanding noise is great, and it can be like completely catastrophic noise of all these different types, and it's still good enough to help you withstand it. I say it can be used for lots of different types of measurements, and you can do experiments, and it's great, but because if I don't have the schedule wrong in my head, the next talk is from IBM, I have to say, of course, we simulated this on an IBM quantum device, because who doesn't? You should. But you can't directly do this kind of a thing on a quantum computer, because you need to be able to have a control system that's quantum that dictates the order in which the wires are put on your quantum computer. And currently, we don't have access to that on the IBM machines, but the first time Lucien Hardy was thinking about these ideas, this wasn't called indefinite causal order, but there's a paper from 2006 where he was saying, what if the wires in your computer could be put into a superposition? What could you do with a quantum computer? Turns out there's now a whole field, and these are some of the exciting things you can do. So again, thank you for listening. I'll again thank my team. It couldn't be done without the collaborators. I will thank the organizers for this great opportunity, and now really thank you all for listening.
Thank you for a great talk. We've got questions. We'll start over here. Go.
Thanks for the nice talk, Aaron. So if I may, I'd like to ask two things. One, is this unitary that you use for causal order just a product of two control unitaries, one which is UA times UB, and one that is UB times UA, and one that is a swap?
So yes and no. So just to repeat the question, can you get to the same unitary right from the beginning just by having definite causal order and some controlled unitaries where in the middle you switch out the state of your control? So it depends what your application is. The answer is no for us and yes for some people. The answer is if your application is saying how many times do you have to have a unitary, you might have to worry about doing that because you actually have to check each unitary a certain number of times. If you have noisy operations, you can't do that. Because to do that, you need two versions of your noise operation. So to do this, you would need like an A and then a B and then another A that was waiting, and you'd have to somehow promise that both A's were the same. And
Is
that's
that
okay.
the same pulse sequence in an IBM quantum computer?
Yeah, so if you're simulating it, you can do that. But if you actually want to say, I'm probing one noisy process and I have one noisy channel, there's nobody that's ever going to guarantee that operation A here and operation there are actually the same. And so because of that, if you try and use your setup, you would just get completely depolarized. And you can go through the math with using that exact setup with the control and then swap and control, and you get completely depolarized and you get nothing out. It only works because you have you use the same thing twice. If you had two versions of the same channel and there were two separate versions of the same channel, you would not be able to do this. Yeah.
Other questions?
I think there is a second one.
All right, in this case, we'll let you have a second.
Okay, thanks. And do you know if this has any connection with this DQC1 model where you have one clean qubit and a bunch of garbage essentially? You do a control unitary and then you can estimate the trace. So you're estimating something.
Yes. So the reasons why it work, I would say, are the same interference processes as in DQC1. They're different models. But the thing you get out, because we decided to use a maximally mixed state and you do have a controlled operation, you do get out the trace of the unitary, which is what you get out in DQC1. But the problem is if you have DQC1 and you have all these maximally mixed channels before and after, it could ruin you. And here it doesn't. So I'd say it's similar in style and similar in mathematics, but the interference effects are different.
So let me actually ask something that I fear may just be a rephrasing of part of what Nico is getting at, and it's something that ironically I should know backwards and forwards by now, but I might only know it backwards, which is you said when one of those probabilities is zero, so you have the completely depolarizing channel, this still works. That, if I'm not mistaken, just amounts to comparing a maximally mixed state with that same maximally mixed state plus one rotation, and showing that the way those two interfere is sensitive to the rotation. Is that right, roughly?
Ooh, I still don't think that would be enough for you. If you had a maximally mixed state and you rotate it, you get a maximally mixed state, and it doesn't matter. Here, you actually need the two operations to be happening and the two operations to interfere, because if you just had one set and another set and compared them, I don't know how you want to compare them other than this. But anyway, other than this, you've got no information left. That's a bold statement.
The question still amounts to, right, is when we say maximally mixed state, do we mean the same exact preparation? So when you were talking about the coherence length, the real issue is just that the scrambling operation, you have to go through the same device and at the same time, right? If you go through it at different times and it's changing, this wouldn't work.
Right, exactly. And so when you really think about, let's say we go to this picture, if the mixing A and mixing B are because of some fast dynamics, and it's faster than the time it takes you to get from A to B, then you lose it. Yeah, 100%.
Other questions?
Great talk. I had a question because it seems like the metrological thing you do is on the control, right? You do some single shots. Are you assuming that there's no depolarization channel on the control?
Yes.
How sensitive are you to that?
Yeah, that's a great question. So in my picture, it's literally sailing by. The control depolarization is bad for it, but luckily since it's just a qubit, as long as whatever depolarization happens to the control is not correlated with what's happening to the probe, that might be a bit of a strong statement. But if it isn't, then you just get to say, how much would my single qubit measurement deteriorate from depolarization of my single qubit? And you get all of the regular scaling that you'd ever want. So if your single qubit has a 50% probability of depolarizing, then you then 50% of your accounts become noise and your visibility goes down by that same scaling factor. So it's exactly what you think about for single qubits, and how pure they have to be is what we get for the whole way through.
Or you could have a control for the control.
Right, exactly.
Our time for one last quick question from the back.
Pleasure.
Oh, okay, yeah, thank you. I was wondering, actually two questions in one format. You need this causal order to be there for something that you need to measure. Are there any interesting examples in nature that actually have that sort of causal order in effect right now, for example? And if not, can we engineer the probe system so that it interacts with something that doesn't have inherently that sort of thing, but we design something to interact with it in this way? Yeah.
Yes. So it's a great question. I would say it's all about the second one. So we assume that the stuff exists in the universe with fixed causal order, and then we make our probes interact with them in an indefinite way, and that's what gives us the advantage. So you say that there's this thing you want to measure in the middle here, and it's surrounded by two clouds, and you have to go through a cloud to see it, and you have to come out through a cloud to get it. And we say if you go through those clouds in a superposition of the orders, then you can do well. But the nature doesn't give you the clouds in a superposition of the orders or anything like that. We are trying to engineer a system that can then correspond to this, but the actual dynamics start out as fixed, and that's why I say changing the dynamics just from the stuff we can do without actually changing the dynamics is something legitimate as a new way to find quantum advantages.
All right, with that, we better thank Aaron again.